All right, so today we'll be going over using resistances in heat transfer. So looking at, how to calculate the heat flux through conduction and convection, and then also calculating the overall heat transfer coefficient. And so the best way to start is by looking at this problem that we have here, where we have a house is protected by the exterior environment by brick, insulating material, air, and wood. So the interior temperature is 75 degrees and the outside is 15 degrees. We have the heat transfer coefficients for outside the house and then inside the house because we have that air circulating. So we have that boundary as well. And it appears that we have the K values given below along with the thickness of each material. And so we're asked to find what the overall heat transfer coefficient is, and then the heat flux through the wall, and then finding the temperature between the brick and then the insulating material. Okay, so the first thing that we should do, the first thing would be to basically find or actually draw an image of what we have going on. And so here I'll zoom out, and if we scroll right down, let's draw an image. So what we have is basically we have this wall, right? We have this wall, and we have four material inside of it. So we have, let's divvy this up. So we have this, and this. Okay, and so if we consider this the outside, so let's label this outside. And then if we label this as the inside of the house, we basically have uh, we basically have six different uh, sections. And so let's label them. We have on the outside, we have brick. So we have brick. And then we have insulating material. We have air. And then we have wood. And then we have this kind of like boundary thin convection. So we can call this HI. And then we have the same thing on the outside. And we can call this HO. Okay, perfect. And then the next thing to do would be to label the temperatures, right? So we have the inside temperature as that one is 75 degrees C, and then the outside temperature is 15 degrees C. Perfect. And so we have all the parameters in this drawing that we need. And I think important thing to note is that this is all steady state, so we're not dealing with things changing as time goes on. So these temperatures are constant, and then the properties aren't changing with time, and we have a steady flow going already through this material. Okay, so we have all that information, and now what we need to do is find what the overall heat transfer coefficient is. How do we do that? So basically, we need to start off with the main equation here, which is when we're asked to find what the overall heat transfer coefficient is, we should recognize that overall heat transfer for coefficient. Whenever you see that term, always think of U. Okay? U is what we're usually going to call the overall heat transfer coefficient, not H. That's an individual kind of heat transfer. We're talking about a heat transfer coefficient that's going to encapsulate all of this. Okay, so we have U. What is it useful for? Well, now we can write the equation Q dot. So remember, Q dot is the heat transfer rate. The dot always means that it's a rate. And Q dot is basically equivalent to U times A times delta T. Okay? So this is the relevant equation here. And we identified this by basically looking at, okay, the question was asking for the overall heat transfer coefficient. How do we calculate that? Well, we need to look at this. Okay, so we have that, and then the next equation that we're going to need for this is, the next equation is basically how do we find U? Well, U is equivalent to 1 over A times the resistance total of that system. Okay, so this is the second equation we're going to need. And you can see this equation written as another way. This is the same thing as if you were to write this as Q dot equals delta T over R. Okay, so this would be equivalent. Okay, so now that we have this, where do we go from here? We need to find U, and right now we don't have an A and we don't have a total R. Okay, so our main goal now is to find what our total is because that's the one that we can calculate. A, we're gonna be given, we don't have any measurements of the length or the width of each material, so we can't really calculate the cross-sectional area. So for right now, we're gonna have to deal with unit area. So we're gonna deal with A being 1 feet squared, just one, so per unit. And so our goal is to find our total, and so let's start with that. Our total. Okay. So one thing to note is that for conduction, so this is going to be all for Cartesian. Okay. For conduction, R is equivalent to L over Ka. Okay. So that's what the resistance is for each material. And then for convection, R is equivalent to 1 over HA. Notice how we don't have a thickness here because we're considering it as an infinitesimal kind of boundary layer for convection. All right, perfect. So now that we have this, the second thing that we have to do is figure out, well, are all these materials in series or parallel? Kind of think of it as a circuit, if you have to, where we can have like these materials in parallel, where you have kind of um, in a circuit you have this, um, in which case, in order to get the total resistance, you inverse sum these, or we could have them in series, right? We could go like this and then go like this. And if you think about this, this is basically how we're going to be treating this, because temperature is flowing from hot to cold. So it's going from inside to outside, and it's going through series, right? It's not diverging and splitting into two separate streams. It's all going back to back to back. And so this is a series kind of format, in which case that we just sum up the resistances. So going back to our total, what this means is that we have, let's first work our way from the inside to the outside. And so we have essentially 1 over hi, right, times A plus L, then L sub wood, right, that LW times KW times A. And then we have L air, K air times A. We have that with L insulating. And then we have the brick. And then we have 1 over H naught A. Perfect. So this is our total resistance if we look at this. Okay. And so if we plug in values, what we can get is that uh, we see that 1 over hi, what is hi? Hi was 2. So if we do 1 over hi, we get 0.5. So we have 0.5. And remember, we're using unit area. So this is 0.5 plus L wood divided by K wood. What is L wood? We're given L wood here as 0.5. And so we do 0.5 divided by 0.12. That gives us 4.17. And then we have L air, which is 0.02, divided by K air, which is also 0.02. And so we get 1 for that. So that one is pretty simple. L insulating, K insulating, 0.3 divided by 0.012. And then we have L brick divided by K brick, which is 0.3 divided by 0.38. And then we also have 1 over HO, which is HO is 7, so we have 1 over 7. And so if we write that, let me go ahead and write all of that down. So we have this plus 25 plus 0.789 plus 0.143. And you might be concerned because considering that this one is so high, but it should make sense because this term is correlated to the insulating material, and so it makes intuitive sense that you're going to have the most resistance caused by the insulating material. But essentially, if we add all of this up, we get uh, we get 31.6, and the units for this would be. Let's look at what the units would be. So H has units of watts per meter squared Kelvin. And so this is, or actually, I don't know why I wrote feet squared here. We should erase this. This is meter squared. All right. So 1 meter squared. And so we have watts per meter squared Kelvin times meter squared. That becomes watts per Kelvin. And so what we get is meters per Kelvin. Oh, sorry, Kelvin per watt. Okay. So now we know what R total is. How does that help us now? Well, we have this equation where U equals 1 over A R total. And so what we can basically do is since A is 1, we inverse this. So we get 1 U equals, we inverse this and we get that U equals 0.03 watts per meter squared Kelvin. And so this is how we find the overall heat transfer coefficient. Great. Now we can move on to B, and B is asking now, calculate the heat flux through the wall. Okay, so now that we have this U, we can go back to equation 1, and we see that heat flux equals U times A times delta T. So if we go to B, we know that Q dot equals U times A times delta T. We know what U is, we know that A is 1 meter squared. Delta T is what? Delta T is nothing but 75 degrees C minus our 15 degrees C, which is 60 degrees C. And so now what we can do is calculate what Q dot is as we get 9.99 watts. Perfect. Okay. So now that we have this, we have calculated what the heat transfer rate is. Now we can continue on to C. So find the temperature between the brick and insulating material. How do we do this? Well, we know that the heat flows from inside to outside. So it has to go through this boundary layer, has to go through the wood, has to go through the air, has to go through the insulating to get to this like middle surface. And so what we can do is that we have this equation, right, where Q dot equals U times A times delta T. Well, Q dot is conserved. So the heat flux throughout any of these materials, since it's at steady state, has to be the same. So what that means is that we can sum up all the resistances from this, and this. And what we can do is that figure out what U is from that. We know what the heat flux is from question B. Calculate what delta T is, and delta T should tell us what the temperature here is, because delta T is nothing but 75 minus the temperature here. All right, so let's go ahead and do that. So what that means is that R total is equivalent to 1 over HI times A L wood divided by K wood times A plus L air K air A L ins K ins times A. All right. And then we have those values up here as this. So then what we can do is that we can add them up. And what we get is that our R total is 30.67 Kelvin per watt. Okay. And then we calculate U as 1 over that. So we get 0.03. Once again, we can go 0.003 there. Let me go down. So we get watts per meter squared Kelvin. And then we have 9.99 watts as equivalent to 0.033 times 1, because we're using unit area, and then delta T is 75 degrees C minus X. Perfect. And so what we essentially can do now is we divide 9.99 by 0.033, and then we subtract 75 degrees Celsius. But remember, 75 degrees Celsius has to be converted to Kelvin. So we get 75 degrees Celsius. And then so that is 348. And then we subtract and we get X is equivalent to, oh, what? We get X is equivalent to 45.4.